So we've already talked about kinetic energy. We've talked about kinetic energy being equal to 1/2 mv squared. Now, I already let the cat out of the bag on some of the other videos saying that there's more than one form of kinetic energy. There's actually 3 that we're going to talk about. Depending on the class, that is. I mean, AP, we don't have to talk about simple harmonic, which is kind of a shame. I mean, it really is not all that complicated. In IB, we don't have to talk about rotational. So in either one of those classes, you're only going to talk about one or the other. In honors, we're going to talk about all 3. So, talking about kinetic energy, 1/2 mv squared, the rotational equivalent to that, well, all we need to do is talk about the rotational equivalent of each one of those. Remember, if you go back, and if you need to, go back and refresh yourself by going through the rotational parts of these videos. I mean, there's a rotational section on momentum, there's a rotational section on inertia in the momentum and inertia sections, and then there is a rotational equivalent of motion in the kinematic sections. So when we look at this, we've already talked about the rotational equivalent of m, mass, which is also called inertia, and the rotational equivalent to v, velocity, rotational velocity. Okay, so they're both represented. So when we look at this, we can say that Ke is equal to 1/2. Now the rotational equivalent to mass is what we call rotational inertia, which is expressed by an I. Don't ask me why it's an I. But if we were to look at the units of rotational inertia, so only the units of it, so looking at all of the rotational inertia that we want to talk about, the first one being a mass on an object, you're looking at mr squared. Looking at a cylinder, 1/2 mr squared. Well, the half has no units, so the only units that are associated to rotation rotational inertia is going to be the units of mass, which is a kilogram, a base unit, and radius, which is a meter. So that's a meter squared. So that's the units of rotational inertia. So in order for kinetic energy to translate, we're going to have the exact same units here as we do for the rotational equivalent. So looking at this, mass, kg, this, m squared, v squared. That turns out, by the way, if I haven't said before, is a joule. Okay, that's the unit of energy. Or some people will express it as a Newton meter. Newton meters are typically saved for work, where joules are typically saved for energy. They're equivalent, so it really doesn't make much difference. So I need rotational inertia to replace m. Okay, but that has the wrong units. That has kilograms meters squared. So this is a kilogram meter squared. Well, fortunately enough, if we look at v squared, which is going to be meters per second, so it's going to be meters squared per second squared. When we look at that and we want to translate that into rotational component, we know the relationship between v and omega is that. So when I bring in the rotational equivalent to that, when I bring in the rotational equivalent to velocity, which is omega, and square it, I'm actually bringing in this is going to be equal to v squared over r squared, which is going to give me the units of velocity right here. Oh God, McNeil, what the hell are you doing? Going to give you the units of velocity and these units of additional units of meters, which are going to cancel out here. So it's going to give me the exact same units, kilograms meters per second, or kilograms meters squared per second squared. I guess the proper notation for that would be something like that. Okay, so that is the rotational equivalent to linear energy, 1/2 mv squared. The rotational equivalent being 1/2 I omega squared. I being rotational inertia, omega being rotational velocity or angular velocity. In either case, it's the same thing. Okay, so that's the rotational equivalent of that. Cool?